here we go. Notes. Notes look like this, and we left off over here on this page. This is our last equation. There's only 3 equations. It's actually a really small unit. So we left off with this conservation of momentum, saying that the amount of momentum that's occurring before a collision equals the amount of momentum after a collision. And so, just so that way, because we're on a shorter class period today, I'll skip this part and I'll come down here. Going back to my same colors that I was using yesterday, that yellow and pink, it says over here, you as in you personally, it says that you will need to be able to use this equation that is on the formula chart, and you will need to learn how to modify the equation based on each situation that is occurring. Remember, every time there's a modification, I call those Superhero Power Ranger morphed. You're about to have to morph it. Look at this one, and this one. They're all 3 the same, which looks like this equation we wrote up here. But when I read the math problem for physics and I figure out which type of situation is occurring, I'm going to need to morph my equation so that way my equation, it looks similar to the situation. So first thing, over here, this is going to be an elastic collision. The next one's going to be an inelastic collision, and our last one's going to be an explosion. Remember, and those are the 3 that we're going to focus on for this unit. Those 3 types of collisions. Now, the first one we talked about yesterday is when we have object 1 is going to collide with object 2, and at the end of the collision, they don't stick together. They just bounce off of each other, and then they go their separate ways. 1, 2 equals 1, 2. Now, I just want to make sure that we understand that this is a basic 2 objects colliding. But in real life, we can have 3 or 4 objects that collide. And on the test, we're going to end up with a problem that has 3 or 4. If I have 3 on the left side of the equation, after this, I would put plus M3V3B. And on the right side of the equation, I would put plus M3V3A. Right? I would continue to add it and modify it to fit the situation that's occurring. Now, because I have 1, 2, 1, 2, 1, 2, 1, 2, I leave the equation as is. But for an inelastic equation, for this situation, I have object number 1 and object number 2 are about to get into a collision, and when they collide, you can even see my actual circle is a little bit bigger, right? We're going to talk about that again in just a moment, but we did yesterday. They morph and they smush together. They get stuck to each other in what we call an inelastic collision. On the left side of the equation, I have 1, 2. On the left side of this equation, I have 1, 2. Perfect. On the right side of the equation, I only have 1 thing. But on the right side for this equation, I actually have 2 things. Which side do you want to get rid of? I don't care. But you do need to get rid of one of these. So I'm going to get rid of it. That way, the left side has 1, 2. The right side has 1. What I am going to say, though, is due to the law of conservation of mass, I can't just poof, get rid of the mass. If that was the case, and there was a collision with things that were bouncing off or hitting each other, and mass disappeared, I would be like bouncing off the wall or throwing myself on the ground so I can lose weight. Unfortunately, it doesn't work that way. And since it does not work that way, this mass does not just poof, go away. I'm going to have to get this mass, I'm going to bring it over to this part of the equation, and I'm going to say plus M 2. I will add them together, okay? Okay, last part is the explosion. And on the explosion, you actually start off with one object, right? And my one object, quote unquote, explodes or breaks apart. And when it does that, you can see, quote unquote, here, it gets smaller. But the masses we don't get rid of any of the mass. On my left side, I have one thing. On the right side, I have two things. So here are two things on the right side. On the left, I have to get rid of one of them. Which one? I don't care. I'm just going to get rid of one. But what I cannot get rid of is the mass. So the mass is going to be conserved. I'm going to bring it over here, and I'm going to say plus M1. Plus M1, because they need to be combined together. All right, so now that we went through this part, now we're ready to go ahead and work these math problems out. It's our last math problem. So it says here, when in doubt, you know what I say, draw it out. Draw out these circles if you need to, if you're not sure what type of situation is occurring. Number 2, determine which type of collision it is. Is it elastic, inelastic, or is it explosion? Number 3, modify and morph your equation properly. But do not just poof, get rid of the mass. Number 4 says do some awesome physics and math magic, so that way you can go ahead and get the problem done. And number 5, the last part over here, important. Now, first thing is, we definitely know direction is important because momentum is a vector quantity. I'm going to tell you that I do not care. I'm just going to put a little line like this. I'm not going to, because I have so many issues with a lot of students, and the problem here is that I get students from all different school districts that come to me with all different math skills, and it gets a little tough sometimes. So for this, I'm going to exclude and not even worry about the direction, which would be, for an example, if you're moving south, it would be a negative, right? Because we know it's a vector. What I want from my students right now is that you know that momentum is a vector quantity. When you take university physics, which is physics 1 for college, then at that moment, you will absolutely take those vectors into account. So let's go ahead and do math problem number 1. Okay, and guess what? It sure enough has a actual, what do you call it? It has a direction, east, all right? Now it does have a direction, but you know what? Again, like I said, I know it's a vector. I know that you know it's a vector. I'm not sure, and I know that a lot of my students don't go into university physics, so I don't want to stress you out. So I'm going to ignore vector directions. But what I am going to say, though, is that my car, number 1 over here, which is mass 1, has a mass before and after is going to be the same. So if you want to put M1B or M1A, that is up to you, because remember, mass never changes. But it says here, 400 kilogram car is traveling east at a velocity of 30 meters per second. This velocity, though, is important. Not only does it correlate with my object number 1, so I'm going to put a 1, but it's before any type of collision, so I'm definitely going to put a B, because that part is important. It crashes into a parked car. Now, this parked car, which is object or mass number 2, is parked. And remember, in physics, words have a number value. So this is going to be velocity 2 before the collision. The two cars crush together. That is a key word. Crush together means N elastic collision. How fast is the crash moving after? What is the velocity of 1 plus 2 after the collision? And why did I say 1 plus 2? Because those two things crush together. Okay, they crush together. Alrighty, now that we got this done, let's go ahead and let's get our math equation. Our math equation looks like this. It's a traditional equation, and then we will have to morph it to fit our situation. What I would like to do is I would like to grab the formula chart. Somebody had a really good question last class period. Miss Munson, what does it look like? Well, on your formula chart, we have the momentum equation, we have the impulse equation, but it also says the law of conservation of momentum, and you can see that this is the actual equation. You will need to modify it for the situation that's occurring. So I'm going to go ahead and write it out. M1B, MV1B plus M2B, V2B equals M1A. And again, I don't have to put an A or B for the mass because it will always be the same. V1B, I'm going to add that to A, forgive me, because this is after the collision. M2A, V2A, right? The before versus the after. Well, we just said this is an inelastic collision because they smush together. So for this situation, I need to get rid of one of these sides because what I have is object number 1 plus object number 2 are going to collide, and they are going to equal object 1 plus object 2 that's going to combine into a inelastic collision. So I need to get rid of something over here on the right side. What part? I don't care. So I got rid of that, but what I cannot get rid of is the mass. This mass is going to come over here, and I'm going to say plus M2. And remember, the mass before is the same mass after the collision. Let's go ahead and put our variables in. 400 multiplied by 30 plus 200 multiplied by the parked car, which is 0, equals 400 plus 200 multiplied by the velocity of 1 plus 2 after the collision, right? Because they collided and now they became one smushed car together, one big mass. Okay? Or if you feel more comfortable, you can just say VA. You can say that because you know that the two masses were smushed together. Let's go ahead and let's continue to do our math over here. 4 times 3 is 12. Don't get rid of those zeros, so 12,000. This 200 times 0 is 0, so I'm just going to put an X over that. Equals 400 plus 200 is 600. And the V after the collision, which is car 1 and car 2 because they're inelastic. Algebraically, you can see that you're going to divide by 600 to cancel. Divide by 600. My velocity of both car 1 and 2 after the collision is 20 meters per second. Done. All right, that is our last math equation. When you're ready, let's turn the page and let's try this again. I'm going to go to that question with the monkey. Let's do the monkey. Do you see that question? It says the monkey. Let's do that. All right. It says here that there's this monkey that's running. Well, they gave us a mass and they told us it's a monkey. So that's already going to be object number 1. So I'm going to call this in its mass, so M1. The monkey is running east. Again, I definitely know that that's a vector regarding direction, and it's traveling at a velocity. There has been no collision yet. So this is V1B. I definitely need to distinguish my velocities before and after. Now Bob is a different object. And so Bob has a mass, which is m2 of 75. Bob is standing still. Oh, I love it whenever physics has words that mean values, number values. V2B. And not paying attention. All of a sudden, the monkey jumps and latches onto the man. The word latches means an elastic collision. So I'm going to write that in for myself. And knocks him over. What is the velocity of the monkey on the man's back after they collide? Question mark. What is the velocity of object 1 plus 2 after the collision? Or you can just say VA, because now they're combined into one. Okay, here we go. Let's do this. Before I go any further, I'm just going to do myself a little picture drawing. The monkey and the man. They collide, and now they become one inelastic collision, and we're going to call this a monkey man. Right? Because they stuck together and they collided and hit the ground together. So my equation, which is M1 V1B plus M2 V2B, and I only have two objects, thank goodness, equals M1 V1A plus M2 V2A. And I know that I need to get rid of one of these on the right side because I have two objects on the left, one object on the right. Which one do I get rid of? Who cares? Just get rid of one. The thing, though, is we cannot get rid of mass due to the law of conservation of mass. So I'm going to bring the mass over here, and I'm going to say plus M2. All righty, here we go. So for this situation, I'm going to come over here, and I'm going to say, let's plug in our numbers now. 30 times 7 plus 75 times 0, standing still, equals 30 plus 75 times the velocity after the collision. All right? Let's go ahead and let's do this. I love it when we have zeros because I can cross that out. 30 times 7, 30 times 7 comes out to 210. Equals 105. Double check my math because I did the 105 in my head earlier today. Times VA. Divide by 105. Cancel. Divide by 105. The velocity of object 1 plus 2 after the collision came out to blank meters per second. Not bad. Oh, 2? 2 point something, 2.5? Oh, just 2. Oh, okay, gotcha. Just 2. Not bad. Easy cheesy, I think. We've got a couple more. Let's practice. Let's do this tennis. Alrighty. We've got a 3-kilogram tennis racket. It's moving 12 meters per second. It hits a tennis ball. Oh, well, let me go ahead and let's start this. This is M1, and here is V1B. Now, here comes along this tennis ball, M2, that is moving at this velocity, V2B. After the collision, oh, there's a collision. Well, I'm pretty much familiar that a tennis ball is not going to stick inside of that racket. So I'm going to call this, there's a collision, and it's going to be an elastic collision. Afterwards, the racket is moving. Whoa, let's go over here. Racket was number 2. So its velocity after the collision is 6. How fast is the ball moving? Oh, forgive me. The racket is over here. Racket is object 1. The ball is object 2. V2A. There we go. Question mark. Alrighty. So object 1 collides with object 2. 1 plus 2. And they do not stick together. That is going to be our traditional equation where there is no modifying, no morphing, and no changing. Leave the equation as is. So let's do that. M1V1B plus M2V2B equals M1V1A plus M2V2A. There we go. Let's plug in our numbers. 3 times 12 plus 0.06 times 22 equals, the mass never changes, so the mass before and after are the same. 3 times 6 plus 0.06 times the velocity of object 2 after I do not know. So if you've already started working on this, hopefully this is what your setup looks like. Go ahead and do the math. This would be 36. I don't have the numbers in front of me, so let me get my calculator out. 22 times, 0.06. I get plus 1.32 equals, what's this, 18? I'm that bad. 0.06 V2A. Okay, 36 plus 1.32. This comes out to 37.32 equals 18 plus 0.06 V2A. Whew. Please excuse my dear Aunt Sally. I said that last semester. Super important, critical to follow those steps of order of operation. Now, if we follow those steps, picking on Mr. Anderson in the back, Mr. Anderson, what is my first step to do? Thank you. Thank you. Hopefully we all agree. Subtract 18 on both sides. Take away 18. This comes out to 19.32 equals 0.06 V2A. Divide by 0.06, cancel. The velocity of object 2 after the collision is 322 meters per second. Whoa. Easy cheesy. We got this. We got this. Alrighty. So other than that, we've got, you need to practice. Please, please practice. Over here for this question right here, we've got an elastic collision. At the top, we have an inelastic collision at the top. Then, we grab a little marker over here. On quiz 1, this math equation will not be on quiz 1. But if we turn the page back up to this point, momentum, impulse equation, and being able to read situations and telling which type of collision is going to be all included for quiz number 1, including homework 1, 2, and 3. Okay? So there you go. I really wanted to make sure it was very cut and dry. You knew what's going to be on quiz number 1.